So in this video, we're going to get started with current, resistance, and Ohm's law. And let me make it full screen because I think it'll be easier. So we'll talk about batteries. Batteries provide chemical electricity. Now they're still electrons. It's nothing different. It's just that there's chemical reactions. So you can see that the electrons, they kind of bunch up over there on the left side of the battery there. Point with my cursor here. There we go. And they want to flow. They have what's called the potential to flow from the negative to the positive. Now remember, potential is voltage. And then on the other side is another chemical reaction. There have to be two chemical reactions, an oxidation and a reduction. For those of you in AP chemistry will know that. Now electrons don't flow in an isolated battery. If you have a battery sitting around in a drawer, the electrons are not moving. There's no real chemical reaction going on. You might say, yeah, but sometimes batteries get old and you have to throw them away. That's because of chemistry. That has nothing really to do with the physics and the electricity. The electrons haven't moved anywhere. It's just the chemical reactions kind of aged themselves out. So in order to flow, you have to have a complete circuit. And the best example is operation. If you've played the operation game, I'm sure we all have, and you're picking out the little bones and parts, you don't get the buzzer until you accidentally touch the side of the metal tweezers to the metal. Because then when you do that, you have a complete circuit. The electrons can flow and the buzzer goes. And you have to have a battery in there. Before it, the battery was not moving at all. Now, we often think about electrons flowing like water. We use that metaphor all the time. But it's not a perfect metaphor. Electrons don't really flow through wires like pipes. The electric field gives direction to the random motion of the electrons. So what does that mean? We have to have positive and negative in order to have an electric field. So you set that up with a battery or a power source. Now the electrons will flow towards the positive end. And we call that the drift speed. Now there's equations to calculate things, but we won't. We'll just say that the electrons move at 0.05 millimeters per second. Believe it or not, electrons are really slow. They only go about a year in 1 mile. You or I could easily walk a mile in 20 minutes, maybe quicker if we really hustle. So you say, well, how do the electrons move, or how does this happen? Think about the coin waterfall at Chuck E. Cheese or in an arcade. It takes a long time for any one quarter to move, or the tokens to move all the way on that coin waterfall. But every second, it's pushing the one in front of it, pushing the one in front of it, pushing the one in front of it. So it takes the electrons about 5.5 hours to travel 1 meter. So each individual electron is really, really slow. However, you say, but I turn the light on and it's almost instantaneous. Yeah, because, yeah, that one electron doesn't move, but it moves the one next to it. It pushes the one in front of it along. It's kind of like the dominoes when you set up the dominoes and you knock it over and then they keep going. So overall, electrons are really slow, but electricity itself is really, really fast. And we're going to see that in the next slide. Now, conventional current. We use what's called conventional current. We think about things flowing from the positive to the negative. See it go around in the wire there? But that's not really what happens. In actuality, the electrons move. Positive charge can't move. Positive charge is caused by the protons, and they're the atoms, and they don't move. They just sit there in their nucleus and never go anywhere. So it's actually the electrons that move. Now, surprisingly, current itself flows at somewhere between 50 and 90% of light speed. So the current that we think about, those electrons bumping against the next one, that's how it moves. But if you look at that drawing there in the lower right-hand corner, the current seems to be moving counterclockwise. That's the conventional current. The electrons themselves will move, current's going clockwise, but the electrons would go counterclockwise. Sorry, I was saying it the wrong way. So there's the conventional current going around. But the electrons actually go in the other direction. So you can see that they oppose one another. In that little cartoon kind of drawing I have to the right, we're seeing the electrons going kind of like racehorses around a track or runners going around a track. But the conventional current is going in the opposite direction, from positive to negative. So that's really what we want to think about. We sort of pretend the positive charge moves, even though it can't really. And what's a day without math? It's like a day without the sun. So current is the net amount of charge per time. And the unit for current is the ampere. It's 1 coulomb per second. Now think about speed. We think about speed or velocity as change in distance over change in time. Well, current is a change in charge per unit time. And it's really, here's the secret, it's really a derivative. It's actually dq dt, the change in charge depending on the change in time. Now that's for people in calculus. We're not going to be doing the calculus in here. We're only going to use that top formula. So I think we'll do a few problems and we'll wrap the video up. So we have to see how to apply that I equals change in charge over change in time. Remember, the Q is the coulombs, and we do our problem, we have to do it in seconds. So a steady current of 2.5 amps flows through a wire for 4 minutes. How much charge passed through any point in the circuit? Well, let's see what we know. And 2.5 amps is a pretty big current. That's you don't have that flowing like through a cell phone, or not usually. That's a pretty strong current. So we have those 4 minutes. Just like everything in physics, MKS, meter kilogram second, we've got to convert the 4 minutes over into seconds. So that's what I'm showing there. 4 minutes, 60 seconds, 240 seconds. Then we can say, well, I is change in charge per change in time. You know me, I like to do the variables first. So we're going to multiply both sides by delta t. So the current is 2.5 amps. The change in charge is 240 seconds. So that works out to, let's see, 6,000 or 600 coulombs. Now the problem is we don't really have a feel how much 600 coulombs is. We might be more interested in, well, how many electrons is that? No problem, we can calculate it. Now one little electron is 1.6 times 10 to the minus 19th coulombs. And it'll appear on the screen here in a second. That's the fundamental charge. The charge on one electron or one proton is as small a charge as can exist free in the wild in nature. And then knowing that, we're just going to do a conversion. So there's our fundamental charge. Now we knew, I believe it was 600 coulombs. One electron is 1.6 times 10 to the minus 19th coulombs. And that works out to 3.8 times 10 to the 21st electrons. That's not quite a mole of electrons. For those of you in chemistry or remember your chemistry, the mole is 6.022 times 10 to the 23rd. But we're getting close. That's quite a number of electrons flowing in that 4 minutes because the current was so high. And we'll see another example, and this will be the last one. So now we'll reduce the current a little bit to 1.9 amps. And we say, well, how long to get 2280 coulombs? And there's nothing special about that number. I'm sure we just picked it because it was an even number. So we're going to go back to our formula. I is delta Q over delta T. And we want the time. So we're going to rearrange the formula, do a little bit of algebra magic. Delta Q is, or T is delta Q over I, 2280 coulombs over 1.90 amps. And we get kind of a big number there because we're going to calculate it in seconds. So delta T, 1200 seconds, but let's make that into minutes. It's 1200 seconds. It's much easier for us to say 20 minutes. That's what we would prefer. Now we might also be interested in how much charge flows each hour. So I is delta Q over delta T. And we want the Q. We're not always solving for Q, but I think we've seen that a couple times today. So multiplied both sides by delta T there. Current was 1.9. We have to be in seconds, 3,600 seconds. And 6840 coulombs. That's the change in charge. You can imagine the little electrons going by like runners in a race, if you're watching a marathon. And then it's a pretty easy matter to convert all that over into, well, how many electrons flow? Because we know one electron is 1.6 times 10 to the minus 19th coulombs. And let's see what that is. 4.28 times 10 to the 22nd electrons. So we're getting close to a mole of electrons flowing in an hour through that particular circuit.